Okay, hello everyone, welcome back. Today we continue discuss about the topic of the tree. Last time we have been talk about the binary tree and their common operations. Today we're going to focus on the particular type of the binary tree called the binary search tree. So what's a binary search tree? Binary search tree is a binary tree where each node satisfies the following properties. First, all the value of all the nodes in the left subtree is less than the node value. Second, the value of all the nodes in the right subtree is greater than the node value. Third, both left and right subtree are also the binary search trees. Okay, so let's look at some examples. Let's check whether this binary tree is a binary search tree or not. First, let's look at this example. 1, 7, 6. We only have what? Only have the two level, right? The root. On the root level, have a node is 7. On the left child, it's a node 1, which is less than the node 7. On the right child, in node 6, this is not greater than the node 7. So this is not binary search tree. Okay, let's look at this example. So in this binary tree, we can see on the left, okay, this is root node. On the left child, it's a node 12, which is greater than the node 10. So it's against of the first property. So this is also not binary search tree. What about this tree? Okay, in this tree, the root node is 20. So on their left child, it's a node 10, which is less than 20. And on right child, it's node 30, which is greater than 20. Okay, so this looks like it's okay. And let's continue look at this one. This is a root 10. Okay, on the left child, it's node 5, which is less than node 10. On the right child, it's node 25, which is greater than node 10. But there's an issue within we need to make sure the value of all the nodes on the left subtree is less than the node value. So node 25, which is on the left subtree, but it's greater than the node 20. So this is not a binary search tree. Okay, let's look at this example. Okay, in this example, let's look at this is the root node 8. On the left child is node 3, which is less than node 8. And on the right child is node 10. This is greater than node 8. And for 3 and 10, look as okay. Okay, so on the let's go on the left. On the left subtree, for node 3, they have on the left child is node 1, which is less than node 3. On the right child is node 6, which is greater than node 3. And let's check all the nodes, the value of all the nodes on left subtree. It's 1, 3, 6, which is less than node 8. So the left subtree would satisfy this property. Okay, now let's check the right subtree. On right subtree, for node 10, they have the left child. It's node 7, which is less than node 10. And they don't have the right child. Let's look at all the node on the right subtree, which is 7 and 10, but 7 is not greater than 8. So this binary tree is not binary search tree. So the answer is no. Okay, let's look at this example. Single node, node 8. Is this a binary search tree or not? The answer is yes. So single node is always binary search tree. Okay, single node is always binary search tree. Let's look at this example. We call it called a crude tree. Okay, called a crude tree. So in this case, so the root node is 20. They only have the left child. Okay, they only have a left child. So root 10 only have a left child. So we just want to make sure on the left subtree it's less than root node. Okay, on the left child, root 10 is less than 20, which is okay. And node 5 is less than node 10, okay, which is fine. And look at both node 5, node 10, they're all less than node 20. Okay, so this tree, it is a binary search tree. What about this one? This is a right crude binary tree. Okay, right crude binary tree. Let's look at they only have the right child. Okay, so let's look at the root node 20. Their right child is 30. So 30 greater than 20, which looks okay. And 35 is the right child of 30. 35 is greater than 30. And both 30 and 35 is greater than 20. So this is what? This is a binary search tree. Answer is yes. Okay, let's look at this tree. This is the binary tree. Let's look at the value. So the root node is node 8. They have the left child and right child. On the left child, it's node 3, which is less than node 8. On right child, it's node 10, which is less than node 8. Okay, so on the node 3, they have the left child node 1, less than their root node of 3. And the right child, it's node 6, it's greater than node 3. Okay, so on their left subtree, this is a binary search tree, and all their node less than 8. Okay, 1, 3, 6 less than 8. Okay, let's look at the right child. On the right child, they have the node 10, which is greater than 8, and for node 9, it's a left child of the node 10, which 9 is less than 10. They don't have the right child. So node 9 and node 10 are both greater than node 8. Okay, so on the right child, on the right subtree, all the nodes on the right subtree is greater than this node value. So this tree, it is a binary search tree. We also call this kind of tree is what? Called balanced binary tree. So they also it's a balanced binary search tree. Now let's look at this example. Okay, so the root node is 20. The 20 have the left subtree and the right subtree. On the left subtree, node 10, the left child node 10 is less than 20. Okay, it looks fine. And then for node 10, they have the left child and right child. Left child node 5 less than 10. Right child node 15. It's greater than 10. And all the nodes on the left subtree 5, 10, 15 less than 20. Okay, so it means on the left subtree satisfies the property of the binary search tree. Now let's look at on the right subtree. On the right subtree, let's look at the root node for 30. 30 is greater than 20. For node 30, they have the left child 25, which is less than 30, and the right child, which is 35, which is greater than 30. So on the right subtree of the node 25, 30, 35, which are all greater than the root node 20. So it means this tree, it is binary search tree. They also call the perfect binary search tree. I have one question here though. Is there a duplicate key on the binary search tree? To think about that, is there any duplicate key on the binary search tree? The answer is no, because on the property for binary search tree, they're either less or greater. So there's no case for equal. That's why there's no duplicate on binary search tree. Okay, let's look at some of the common operations on the binary search tree. First, it's a search function. To process a search on the binary search tree, you follow the binary search tree properties. So binary search tree properties, what's the binary search tree properties again? So the left subtree less than the root value, for root value less than the right subtree. So based on this property, we defined for this step to process search. So start at root. If the current node value is equal the target value, so it means what? They found this target value. So it means return what? Return the true. If the case target value less than the current node value, the search going to the left subtree. So in this case, going to ignore the what on the right subtree. Okay. So if the target value greater than the current node value, so search going to process only for the right subtree. So the left subtree going to be ignored in this case. Okay. So if you process the entire search, finish the entire search, you reach into the non-pointers. It means you couldn't find the target value. It means it's now found. Okay, this search to be returned false. It's nothing found for the target value. Okay, so based on this logic, we can see, compare within the general binary tree search. Okay, so they have the case, right? They have a case to comparison. Okay, have a comparison. So they can ignore the either left subtree or right subtree. So to process a search in binary search tree to improve the lot on the efficiency, compare with the general binary tree. Okay, let's look at the code. So first, it's using recursive way to process a search. Okay, let's look at code in the how we can apply the recursor into the process search in binary search tree. Okay, so first we check what? Check whether this tree is empty or not. If empty, just return false. It means nothing can be found. Okay. Otherwise, we determine whether this value, okay, the key means the value, okay, the key value whether equal to the target key value. If yes, this means this key is found, able to found. So it's return what? Return true. Otherwise, if a key value less than the root key value, we process what? Process the left subtree. Okay, so we recursively call and root point to the left. All right. So in this case, the root becomes a left subtree. Okay. Otherwise, they process only into the right subtree. So we recursively call the root right and try to process whether they can find the any key value in this tree match the target key value. Okay, that's the way to process search in recursive. Here is the process search in binary search tree by iterative. In the iterative way to process search, we're using the while loop function. Okay, using while loop. For while loop, we pass over the root node. We will compare whether this root node key value match the target key value or not. If yes, what is the return? It means if yes, it means the key is found, right? Found in this tree, we will return true. Otherwise, if the target key value less than the current root key value, we'll be just focus on searching the left subtree. Otherwise, we'll just focus on the right subtree. Okay, for this while loop, if this within this while loop nothing is found, okay, so we return what? Go to this code, right? It means nothing is found in this while loop, which means this key unable to found is not found in this binary search tree, which is return false. All right, let's look at the example. So this is a binary search tree. We just see on the pure slides. For example, if you want to search 15, okay, want to search 15, check whether this 15 in this binary search tree or not. What we do will be comparison from root node. Okay, 15 less than 20, right? So we go to left. Okay, go to left, compare within the node 10. 15 is greater than node 10. They go to right. So for on the right, this node 15, they find the match value. It means they found the value of 15. We found this node. If they process search 27, okay, they want to check 27, was it 27 in this binary search tree or not? What they do here, they do compare with 27 for this root node 20. 27 greater than 20. What they do is to be go to right. Okay, go to right. And then we compare 27 and on their right subtree root node, which is 30. Okay, compare with 30, 27 less than 30, they're moving to the left. Okay, moving to the left. On the left, so for the left, it's a node 25. Node 25, so they compare with 27. 27 greater than node 25. So there'll be search on the right of the node 25, right? On the right of the subtree of node 25, but on the 25 there's no right child. So it means what? Means going to a non-pointer. Going to non-pointer, it means what? The search is finished. So it means they are unable to find the 27 in this binary search tree. So it means return is false. Okay, so they give the null. They give the what? It means null found. Now let's look at the time complexity of the search in the binary search tree. Okay, for recursive search, let's recall this function again. For recursive, what a recursion relation for this recursive search? In this recursive search, we get the one comparison, right? Mainly focus on here, one comparison, and then we search call the half of the node. So the recursion relation will be Tn equal to T n over 2 plus C plus a constant including this, and this comparison. Okay, so this is typical divide and conquer recursion. In this case, we have been did many times regarding for this recursion relation, right? So the big O is log 2 of n. Okay, the big O is log 2 of n. This is the average case, right? What's the worst case? So the worst case when it's a tree is a crude binary search tree. It means you have to go through the entire of the node. So the worst case, you need to go through the entire of the node. Let's turn into the big O of n. But we can see to compare within the other binary search tree, compare within the general binary search tree, the time complexity improve a lot, right? Going to the log n, right? So it means that in binary search tree, the searching process is very efficiency. Now let's look at the iterative search. Let's look at this code. The number of iteration, number of the while loop, based on what? Actually, based on the height of the tree. Okay, based on the height of the tree. We just did a coding assessment last week, right? To get the height of the tree. So for in the binary search tree, the height of the tree we can get is also the based on what? Based on log, right? Log 2 of n. So we can get the big O of log 2 of n. This is the average case. The worst case is the height of the tree. It's what? It's a number of the node plus 1. This means the crude binary search tree. So it means that all the node will be going to be visited. So the worst case, big O of n. Okay, so it means this is not a DP, right? So for convert from the recursion into the iterative way, so the complexity won't be improved. So it's keep as the same. Okay. Let's look at the traversal for the binary search tree. Have the same example, save binary search tree. Look at here. Let's process the bright force traversal. For bright force traversal, what do we get the bright force traversal? For bright traversal, we get 40 and then 20, 60. Then going to the third level, right? 10, 30, 50, 70. The level order, level by level, right? First level is 40, and then from left to right is from second level from 20 to 60, and then we visit the third level, 10, 30, 50, 70. Okay, this is bright force traversal. Okay, let's look at the depth first traversal. Depth first traversal, we have been discussed the what we call the pre-order, also post-order, also in order for the binary tree. We have 3 types of traversal. For the pre-order traversal for the binary search tree, what do we have here? For pre-order, going to parent and then their child, right? From left to right and up and down. So first will be 40 and then go to 20. 20 they have the child and then 10, right, on the left child, and then with the right child 30, and then they go into the right. Okay, going to the right, so 60, right? 60 is their children, 50, and then go to 70. This is a pre-order traversal. And then post-order. What's a post-order? Post-order going to visit the children first from left to right, and then visit back their root, right? Their parent node. So it's from what? From node 10, 30, and their parent 20. And then going to the 50, 70 to 60, and then to the root node 40. Okay, now let's quickly to look at the in order. For the in order, what do we have here? In order, how the in order works in the binary tree. In order will be the left child, and then node, and then right child, in this order, right? So from in order, what we get? 10, and then go to 20, then go to 30, and then go to finish this left child back to their parents. Okay, it's 40, and then going to the 50, 60, 70. Okay, so in order will be 10, 20, 30, 40, 50, 60, and 70. So for the in order traversal, it gives what? We can say gives a sorted sequence. So for binary search tree, the in order traversal can provide the sorted sequence. So this is the most important traversal in binary search tree. Okay. So another important thing for the in order traversal is they use the in order traversal to prove whether the binary tree is a binary search tree or not. Okay, so if you want to check or prove whether it is a binary search tree, you can use the in order traversal to verify it. If in order traversal is a sequence, you can get a sorted sequence, which means this is a binary search tree. Okay. Let's recall the in order traversal, the code. What time complexity for in order traversal? Because this is need to visit all the nodes, so the time complexity is big O of n. Okay. So for all other traversal, you can review on the previous lectures. Okay, now let's discuss about the insertion on the binary search tree. For insertion, here's the step. If we want to insert a value into the binary search tree, so first, if the value is less than the current node, we go left. If the value is greater than the current node, then we go right. We're going to repeat until you find the correct non-spot and insert there. If the value is equal to the current node, we'll do nothing, because there's no duplicate node in the binary search tree. Okay. So for the, as you can see here though, for the all operations after you processed this still the binary search tree. The property cannot change the property of this tree. Okay. So based on the steps, let's look at the code. Okay, so first, it's using the recursive to process insertion. Let's look at code together. First, if this is a empty tree, we just insert at a non-spot, just insert a non-value. Okay, so as we know, so single node is also the binary search tree. Okay, so if there's empty tree, we just insert its node itself. Otherwise, will be check whether the insert key is less than current root key value or not. If less, will be recursively called to the left. Okay, so root left equal to insert has been called function itself, right? To recursive call is going to recursively call but pass the root left. Otherwise, it's going to process the root right and a recursive call on the root right subtree. So if the case we find the key, okay, so if we find the key in this binary search tree, we do nothing, okay, because not a lot of duplicate keys happened into the binary search tree. So it means nothing to be inserted if there's a key can be found in this binary search tree. And then we're going to return the root, right? We're going to return the root. So this is the way to process in recursive to do the insertion. This is doing the insertion by iterative way. On the iterative way, so first we know if this tree is empty, we just return the new node. Okay, this new node is created by this key itself. Otherwise, what we need to define the parent node and the current node. In this while loop, we define the parent node equal to current node from the root. If the key value, which is insert key value less than current key value, we go the left. Otherwise, we go to the right. If this is equal, okay, so it means what? Return the root. It means not duplicates allowed. Okay, after this while loop, what we can get though after this while loop? After this while loop, we find either we find where the spot we're going to insert, right? Okay, so let's compare. If the key less than the parent key value, will be insert to where? To the left child for new node. Otherwise, we're going to insert into the right child. Okay, so that's how it works. Let's look at the type complexity. So for the both cases, the type complexity based on what? Based on the for the type complexity for insertion, it will be the same as search because this process a similar functionality as a search. Okay, so for the insertion, the type complexity will be the big O of log 2 base 2 of n. Which is the average case. The worst case, again, it's the crude binary search tree. It gives the big O of n. Okay, now let's look at the deletion. For deletion, there are mainly have 3 cases. First, the node has no children. It means the leaf node. If you plan to delay the leaf node, just simply delete it. Second case, it means you have a node has 1 child. In this case, what you have to do is replace the node with its child. Case 3. So the node has 2 children. So the node have two children, going to replace the node value with either have 2 options. Okay, option 1 to replace within the in order successor. It means the minimum in the right subtree. Second option is the in-order predecessor. So it means the maximum in the left subtree. And then we delay that successor or predecessor recursively. Okay, let's look at example. Okay, let's look at example. Try to understand this concept. For example, this is a binary search tree. Okay, let's process initially like in order. So from in order, we can get the 10, 20, 30, 40, 50, 60, and 70. Okay, so we can see this is if in order traversal, we get the sorted sequence. So we can prove this is what? This is a binary search tree. Okay. Let's look at the first scenario. Just delay the leaves. For example, delay the node 10. So we just find the node 10 and remove it. Okay. Second scenario. So any node only have one child. So for example, let's delay the node 20. So for delayed node 20, we just find the node 20 and find their child of the node 20, which is node 10. And then we just replace the node 20 within their child, node 10. Okay, that's it. For third scenario, to delay the node have two children. For example, delay 50, the root node. Okay, delay the root node. How can we process? So option 1 is in order successor. So it means what? Smallest node on their right subtree. Okay, if we want to delay the node 50, for the option 1, we first go to the right child. 50, okay, the right child is 70. Okay, find the leftmost descendant is what? Is 60. And then just replace the 50 with 60. And then delay this 60. Okay, replace the value 50 from 60 and then delay the 60. Okay, so in this case, we can keep the binary search tree as still the binary search tree after deletion. Okay. Okay, for option 2, it's in order predecessor. For the in order predecessor, we need to find the largest node on the left subtree. Okay, so this is a step. So if we want to delay 50, we go to the left child, which is 30, and then to find the rightmost descendant. Okay, rightmost descendant so far is what? 40. So after 40, there's no child for 40. So this is 40. And then we just simply to replace the 50 to 40 and then delay the 40. Okay. This is a two option to delay the node which has two children in the binary search tree. So for all these operations, insertion, deletion, after the process, after this operation, they need to make sure still keep the property of the binary search tree. Okay. For this case, okay, they have two options, but the most implementation choose what? Option 1. Okay, choose option 1. successor, okay, to choose the in-order successor to the option 1. Usually to find go to the right subtree, find the last most descendant, and then to replace it. Okay, this is the code. It's a pretty long code. I suggest you can pause here to read the code, okay, to read the code. But now let's just go through together, okay? Let's go through together. Okay, let's look at the main function for delay the node. For main function, okay, so here's a pretty basic case apply for all the operations. If the empty node in this tree, the return for deletion will be return nothing, okay? So it's nothing to be delayed. Otherwise, what they do here to process recursor, okay, to find where to search the node you want to delete. Search a node you want to delete, okay, in this part. Either if the key is less than root key value, we go within the left subtree. Otherwise, we go in the right subtree. So in this step, we can ignore in this case, ignore the right subtree. In this case, it will be ignore the entire left subtree. Okay, so it's improved efficiencies to process deletion. If you're able to find the node, okay, able to find the node which you want to delete, we can find which case is to apply for the scenario. First scenario, case 1, if you have no children, we can check, okay, whether they have the left child or right child or not. If they don't have any children, they just delay this root and return the non-pointer. Okay, and then we can check either they have the left child or have the right child. So this means they have a case for one child case. So if they have what? They have the root left, it's it's none, right? It's root left is now none. It means what? They only have the root left is none. Okay, the case root left none. It means they only have a right child. So we can set the temporary pointer to point to the left child. We delay the root and return the left pointer. Okay, if the root being delayed and left returns the value, just replace that value. This is the case for what? To have the only have the left child. Okay, so the same step. This is to have the case have 2 children. If you have 2 children, we process the in-order successor option. For the in-order successor option, we have the help function to find the minimum. To find the minimum of this binary search tree. So we just pass the right subtree to find the minimum value, and define into to find the minimum node, to define this successor pointer point to the minimum node, and then we replace the key value and then process deletion. Okay, process deletion. This is recursively call this function to delay that value. Okay, so this is the root right subtree, and this is the value we're going to delete. All right. Okay, this is the entire function of deletion for the binary search tree. So please read and try to understand. Okay, please read and understand this code. What about the time complexity for deletion? Will be same as search and same as insertion. Will be big O of log 2 of n, which is the average case. The worst case, it will be the screwed binary search tree. So the big O of n. Okay, the complexity big O of n for worst case. Okay, this is all for the binary search tree. Next topic, we're going to discuss about AVL tree. Okay, we're going to discuss in the next lecture. Thank you.